Welcome everyone. So this is the Extragalactic Astronomy 2 of the ASI meeting. This is a parallel session of 1.5 hour duration. So the first talk that the speaker can plan the end of the talk. So the first talk is by Raghunathan Srianand. He will talk about intergalactic medium probed by Lyman-alpha forest, clustering and its evolution. So Anand, I will give you a warning after 20 minutes. So that will be a 5-minute warning. And then there will be 5 minutes for questions. You can start now.
So thank you, Ritaban. Can you hear me?
Yes, I can hear you.
Okay, good afternoon. I will be talking about Lyman-alpha forest seen in the spectra of quasars and how one can use it to extract various information related to our cosmology or galaxy formation and evolution of the universe itself. This is the kind of program we have been carrying out for now nearly 7-8 years. And this resulted in 3 PhD works, whose names are given here: Prakash Gaikwad, Vikram Kaire, and Somak Maitra. And basically these in collaboration with Titankar Raichaudhuri and Nishi Kandai. The basic idea here, I will just go through the basic idea behind using Lyman-alpha forest. And without going into the details, I will present various results and what are the implications. If any one of you wanted more detail, we can do it after the talk. Basically, if you look at Lyman-alpha, if you look at a distant quasar and if you take the spectrum, you will notice that there will be Lyman-alpha emission. And if you go to the wavelengths which are lower side of Lyman-alpha emission, you will start seeing large number of absorption lines. And these are thought to be produced by the neutral hydrogen gas, which is in the intergalactic space between us and the quasar. Okay, this is traditionally found in front of quasar, but you have to be aware that any object you observe, which is at a distant universe, will have imprint of material which is present between us and that object. And in particular, the all-pervasive, what we call intergalactic medium, it is seen in the form of absorption. And I have shown different spectra of quasars at different redshifts. Higher the redshift, that means farther the object is from us, you find that the absorption strength is much, much stronger. Basically, the summary is that discrete absorption lines you see in the spectrum of quasars, we call it as Lyman-alpha forest because they look like a forest, and it is mostly produced by neutral hydrogen gas which is present in between us. Typically, what kind of numbers one is talking about? If you look at the weakest absorption line one can detect in any spectrum, that will correspond to a column density of 10 to the plus 12 centimeter minus 2. Whereas the strongest absorption one can detect, or so-called damp Lyman-alpha, one can count up to 10 to the 22 atoms or hydrogen atoms per centimeter square. So it is one of the extremely powerful tool where the dynamic range of detecting gas column densities is 10 orders of magnitude. It is amazing. I think it is the one of the things which we don't realize. If you look at these kind of clouds, what is contributing to this kind of column density? You are talking about several orders of magnitude lower densities compared to the best vacuum you can think of in the laboratories. Okay. So what do we do? Let's do a very simple thing which we understood from our graduate school. If you find any absorption line, you can define some intensity at any wavelength lambda, and usually you know that in the case you will write down as I is unabsorbed intensity multiplied by some optical depth, exponential of minus tau. It is very simple radiative transport equation. But what is tau? The optical depth is nothing but the density multiplied by the cross section and the length over which you are integrating, right? This is the kind of thickness of the gas slab along your line of sight density, and this is basically the absorption cross section. So what you can do is that you can think of neutral hydrogen density as total hydrogen density multiplied by some fraction of that hydrogen which remains neutral, multiply by this. Here what you can do is that, like a mathematician, you can multiply and divide by dz. dl by dz is coming from cosmology. It will tell you that if you give a path length of L along your line of sight, what does it correspond to? The redshift difference in your observations, whatever, right? So if you plug in various numbers and take this dl by dz from your favorable cosmology, in this particular case, I have taken lambda CDM. you can write down tau h1. What is the optical depth of hydrogen you expect if you take all the baryons produced in the universe and uniformly distribute them between galaxies, and what we will get. This is the optical depth you will get. It's amazing. For any typical optical depth, you are getting a value which is like 1.8 into 10 to the 5 if all the hydrogen atom remains neutral. This is one of the strongest probe of how neutral the intergalactic medium is. And you see that if you don't do anything, the optical depth is very high. This goes by the name Gunn-Peterson optical depth. What it implies is that whenever you look at a very high redshift object, you should not see any emission below its Lyman-alpha emission line. Because below that, if universe is neutral, you would not have seen any light coming, because e to the minus 10 to the 5 will be a very small number, right? So nothing will come to you. So this is the basic idea, which tells you that the fact that we have seen absorption lines very much in this spectrum means that the universe is highly ionized. So this is what we started with. If you say that universe is ionized, you can also do one more trick. Then you will realize what drives, what fraction of hydrogen will remain neutral. You can do a simple photoionization equilibrium calculation. You take hydrogen, you have number density, you have photons interacting with hydrogen, it produces electrons and protons. You can write down a rate equation. This is the neutral hydrogen density multiplied by the rate at which you are ionizing is equal to the rate at which you are recombining. So this is kind of ionization equilibrium. Now you do the same trick. You write down FH1 into NH, and this will be 1 minus F times NH. So you can actually calculate. It's very simple equation you can think of. FH1, what fraction of hydrogen which will remain neutral. And if you say that this is a small number, you can neglect 1 minus FH1 square. Then you see that fraction of hydrogen which remains neutral will be decided by what is the density of the region, what is the rate at, what is the recombination coefficient, which depends on the temperature. So density, temperature, and the rate at which you are ionizing. So basically, if you find an absorption line system, and you can, in principle, probe these three quantities: density, whatever recombination coefficient, or temperature, or you can say photoionization rate. So this is what we are going to do. What we have done, what I'm going to show here is that we are going to use simulations. Basically, these are hydrodynamical simulation. We have a snapshot, and you know that in typical cosmology, gas is not uniformly distributed. It is clumped in different regions. And if you shoot a sight line through this, you can actually find out at each location what is the density of gas which is present. Of course, this simulation will also give you what kind of temperature each gas particle is having. So you can actually construct something like a radial profile. This is what is done here. This is the density contrast in the sense that density normalized to the local density. And you can see that this is kind of a line of sight, which is exactly like this. You are going from here to here. What you will see is that density is going up and down with respect to some kind of mean value. This is the kind of temperature in these regions. And you can see one thing which is relevant from this simulation is that wherever there is high density, you also see high temperature. This is what is the thing which people call it as equation of state. And you can also see that these gas particles are not in rest, right? Because they are moving because of the influence of gravity and expanding universe. There are two quantities which governs the motion of this particle. So you can also find out what is the velocity of the particle on top of this Hubble flow, right? You can just look at what kind of velocities they have. In that case, so okay, you can take, what you have to do is that you take this particle, you know what is the temperature, you can calculate what is the amount of neutral gas this particle will have and produce the absorption at this place. Then you look at what is the velocity. If the velocity is plus or minus, you move the particle in the wavelength space, because the Doppler shift, and you will get the profile. This is what is done here. What is done here is that this is the absorption profile. You have to see if your line of sight is passing through a density field like this, a temperature field like this, and velocity field like this. So what is interesting here is that even though you find strong absorption, you would think that there is a strong cloud which is sitting there. But in real space, if you convert that into a real space location, you will find that there is very low, not very high density region is present there. So it's clear that the absorption you see is related to the density field modulated by the local velocity field. So it is a very difficult problem to do. The way one addresses is that you do realistic simulation and produce the data exactly like the way you do in observations, and do various statistics with the data. I'm not going to go into these details, but I can do it in the discussion session. Then what you can do is that you can compare the model which reproduces all the observed properties and derive the parameters of the model as the possible parameters from the real universe itself. So this is what one does. I start with low redshift. I will focus on two issues here. One is at low redshift, which is we mainly focus on redshift below 0.5, where the Lyman-alpha line is actually in the UV. So you have to use Hubble Space Telescope, and we have used archival data from Hubble Space Telescope, which has been compiled by Dunforth et al. And also in low redshift, along each quasar, you can also locate where the galaxies are in the foreground. So you can map the distribution cosmic web in front of the quasar sight line, and you will be able to measure whatever quantities you study in gas in absorption with respect to the galaxy density field itself. So this is the distribution of basically absorption regions which you are probing in the redshift space. Here is the idea of what kind of galaxies which you are studying. Basically, impact parameter means how far this galaxy are distributed with respect to the quasar sight line at different redshifts. Okay, this is basically giving you the completeness of this. So what are the things we try to do? So at this redshift, we run several simulations, and we also borrow existing simulations in the literature, and then try to construct the observable quantities and try to compare with them and try to find the best fit values. So there are three quantities which we study for the best fit. The first one I will focus on is what is known as the photoionization rate. So we try to measure the rate at which you can ionize the hydrogen atom as a function of redshift, and it is possible to do this. And this is our measurement. It is done by Prakash at a couple of years back. And you can fit it with evolution, which goes as 1 plus z to the power 5, roughly, right? So it's clear that you, first of all, you can measure rate gamma H1, and you can also ask what is the rate at which the radiation field is evolving as a function of redshift. I think this is one of the first measurements where one quantifies this evolution with higher precision. Actually, what we can also do is that you can do a theory. You know that how many quasars are there, you know how many galaxies are there, and you know how the gas are distributed in the universe. You can actually calculate what is expected from a standard cosmological model, lambda CDM plus quasar distributions and galaxy distribution. This is the PhD work done by Vikram Kaire. And you can see that we predicted this in 2015, and this matches exactly on top of whatever one measures from the observations in 2017. These measurements as well as this model has an important implication, because before this work, there was a work done by Kohlmeier et al. In 2014. They measured this value somewhere here, which was factor 6 more than what you can think for. So they end up calling it as photon under protection crisis, and they said that there is a big crisis in cosmology. I think we solved the crisis in cosmology because of two reasons. This work, when they did the background radiation and calculated, they missed a considerable amount of quasars which are present, at least factor 2 to 3. And we also see that to measure these from real observations, one has to do much more constrained models spanning wide range of parameter space, which we were able to do with Prakash's during Prakash's thesis with Tirthankar. Okay, so this is the first result. This is that measurement of UV radiation field and solution to what we call as photon under protection crisis. While doing this thing, we realized one of the problems with the simulations, even though we are confident about these measurements, the simulations have their own shortcomings. It is not that simulations produce everything properly. So these are the observed distribution of what is the width of these absorption lines produced in the real universe. So red points shows what you measure in the real universe, and the blue curves show what one gets in the simulation. So we find that the simulation tend to produce absorption lines which are actually weaker, or we can say that we are narrower. So how to make the absorption line broader? You know that one of the things one can think of is to do Doppler broadening. You can say that you can heat the gas a bit more so that the random motions will be increased. And it is possible that you may have to introduce, we found out that whatever physical process one can think of, which can be introduced by radiation field, that does not help you heat the gas. We can think of heating by cosmic rays or any other non-standard heating, which could help. Or we can say that our simulations are done in cosmological setting with minimum dynamical range. So you may be missing some amount of microphysics at the small scale. For example, our pixels will be about 50 kiloparsec, because we are talking about several tens of megaparsecs. So it is quite possible that you are missing this turbulence. So we are unable to address that at that time with the existing simulations. So now there are attempts being made to understand whether turbulence or this cosmic ray heating can be incorporated by different people in the field, not only us. So this is the issue I want to brought out. The third thing which we did is that we asked the question like whether Lyman-alpha forest is uniformly distributed or not. You see absorption lines, you can ask the question, if I go and find an absorption line, what is the probability that I will find one more absorption line within the separation of R? This is what we are doing here. You can count pairs of absorbers and you can ask how many pairs are found with the separation R and how many you expect if the clouds are randomly distributed. And this is what is gone by this defines what is known as 2-point correlation function. Similarly, you can define 3-point correlation function and reduce 3-point correlation function. So these definitions are extremely standard, and one can actually do in our case, since we are doing one-dimensional, we calculate these quantities along the line of sight. So let's target, let's focus on this curve. What is plotted here is that 2-point correlation function as a function of separations. And we find that the Lyman-alpha forest, which was when I was doing PhD, people used to say that there was no clustering. Definition of Lyman-alpha forest is that absorption without clustering, without metals. But this has been now proven to be not the correct statement. So you can clearly see that we detect the 2-point correlation up to 10 megaparsec scale. And we can also now define 3-point correlation. The idea is that if you sit in one particular location, you ask that what is the probability that you will find two observer, one in the right direction at a separation R1, another in the left direction with a separation R2. And this you can again do it like basically you can calculate what is the number triplets observed and number of triplets predicted from the random distribution. Then the actual 3-point correlation function will be defined like this. This is known as probability excess for finding a triplet. Then you have to make the correction for the fact that there could be doublet which will be sort of contaminating this triplet correlation. So we can actually, this is the kind of thing given by Peebles. So we follow the same thing which has been used in the case of galaxies. We follow the same thing for clouds. Then one can define the dimensionless 3-point correlation function as a cyclic combination of the 3-point correlation divided by the cyclic combination of 2-point correlation. These are all standard definitions. What I wanted to tell you is that we actually measure the 3-point correlation at the scale of about 1 megaparsec. And this is the first ever measurement of 3-point correlation of the Lyman-alpha forest reported in the literature. I think the first ever means that is first, right? The second thing is that we can also obtain the value of Q. Again, first measurement. Q measurements are slightly less statistically significant because Q has also propagating error coming from the product of 2-point correlation function. The 3-point correlation function is well defined. In this work, there are two main results we obtained, which I will highlight. One is that the 3-point correlation, the regions which we are finding 3-point correlations are tightly correlated with the galaxy distribution. We can see it in the following way. What is the histogram shown here is that we can actually look at a Lyman-alpha forest. You group them into following. You say the single absorption line without any neighbor. You can say doublets and triplets, right? You can look at the distribution of, and then you look at where the galaxies are. Since we know the galaxy distribution, what is the distribution of nearest galaxy with respect to triplet, with respect to doublet, and with respect to a single absorption? And the red is for the triplets. And you can see that the median value of red curve in all these curves are closer to 0 compared to the green curve, which is coming from the isolated absorption systems. This clearly demonstrates that when you are looking at multiple absorbers, triplets, what we are actually predicting, the 3-point correlation, is coming from the region which is tracing the filamentary structures in the Lyman-alpha forest. Again, this I would say that it took a lot of effort, but this is the first confirmation of connecting what one see in one-dimensional clustering into whatever you see in the 3-dimensional structures in the case of galaxies. It is possible for low redshift because we are dealing with HST spectrum, which gives you UV absorption lines, and we are dealing with deep galaxy surveys. Okay, so this is for the low redshift, and so we can ask the question: can one make this clustering consistent in simulations as well? So this is the plot where the open squares are for observations, and the red and blue ones are two simulations which we used. One thing which is evident is that both 3 and 2-point correlation, if you are at a larger scale, if you are beyond 1 megaparsec, you will find that all points coincide here as well as here. When you are at a smaller scale, we find that observations produce larger clustering, simulations produce larger clustering compared to observations. I think if you remember, I was mentioning that there is a typical tendency in our simulation to produce absorption lines which are narrower. When there are two absorption lines which are narrower, it is easy for us to distinguish between them as a separate entity so that we can calculate the clustering between them. If the absorption become broader, our ability to resolve two absorption becomes difficult because they become merging with each other.
So you have 5 more minutes.
Yeah, I'm okay with that. Yeah, thanks. So basically, this is another problem we have to solve. So in summary, in low redshift, what we have found is that first measurement we reported for 2-point and 3-point correlation function, connection to galaxies. There are issues with in the simulations when we are dealing with small scale in terms of width of the lines as well as clustering properties. Now we move to the higher redshift because in between we cannot do is basically the observational problem because of the our atmosphere. We are unable to measure the UV spectra from ground. But when the redshift is about 2, we will be able to do this exercise more correctly. So I will this slide gives you what kind of data we are using, what kind of simulation one is using. This is the biggest sample of data compiled for high redshift quasars, as well as this is one of the extensive set of simulations from the literature as well as our own for this work. So now let me go back to the same thing. The first thing we start with is the measurement of temperature of the intergalactic medium, because low redshift temperature is not very useful. I didn't mention it in great detail. In high redshift, we can measure temperature. This is the measurement of temperature as the function of redshift. And first thing we notice is that there is a peak around redshift 2.7. It is confirmed at a very high significant level. And this peak is expected if the universe is going through helium-2 reionization. So this one can think of as a proof of yet another proof of helium-2 reionization occurring around redshift 2.9. But not only proof, we can constrain it much better. I'll go into the details. So people measure gamma H1 like we have done in low redshift, and for gamma helium-2 at higher redshift. And several models are proposed, including ours, which goes through these points, so that we have a consistent model of background radiation, which will give you hydrogen as well as helium if you have done only this much of work. But when you now look at what is needed, and in fact, even to do this, we have to tweak a bit. We have to say the following. You have to say that at high redshift, usually the radiation field is dominated by galaxies, and low redshift radiation is dominated by quasar, with a condition saying that suddenly at high redshift, the galaxy should have large escape fraction of UV ionizing photon. We know that in low redshift, most of the UV photons don't escape galaxies. This is another challenges one face, and this is basically been highlighted by several people in the cosmological literature. Okay, so now let's come back to this. You have this measurement of temperature, and you have this radiation field. You think you have already constrained very well. And what do you make? So you put this thing and find out what is the predictions, and these are the predictions. If you don't do anything, you follow the standard procedure everybody adopts in the simulation. So you find that basically the temperature profiles are not as predicted by the models. Observations predict much sharper rise in the temperatures. However, one can make them work by saying that, okay, in the simulation, assume equilibrium, ionization and heating. You actually evolve the temperature and then see what happens. Then you see that actually the range in temperature is increased, but still these curves are not sitting on top of the observational data. So we can tweak one more thing, saying that, okay, you are making some mistake in the calculations. You say that your efficiency of heating, the IgM, as from the standard textbook, is not valid. You reduce it by a factor, scale factor, then you are able to fix it. So couple of take-home points. We measure the temperature. It challenges the existing standard models of evolution in the simulations. We have to introduce two quantities. One is the non-equilibrium evolution of the heating and radiation ionizing field. In addition to that, you have to also say that when you are doing heating, you are not efficiently heating. Somehow you have to manipulate the heating efficiency. So this is very important result, and it puts interesting constraint on the helium reionization. I have a couple of slides where I want to say that the same thing which we did in the low redshift clustering, we also managed to measure the high redshift clustering. I must say that this is once again, very important contribution to the field. Nobody else has done this before. I have to reiterate, because these are PhD work, so it took 2-3 years to do it, but it was very important contribution done by Shaumak Maitra. So here is the 2-point correlation measured at different redshift. With your eye, you can clearly see that there is a strong evolution in the clustering of 2-point correlation function. As you go to higher and higher redshift, the clustering goes down. This is the 3-point correlation function. And again, this is the first measurement of 3-point correlation function at these redshifts. Again, you see that This is decreasing as a function of redshift, and this is the measurement of Q, and its Q of 0.6 is amazingly consistent at all redshift. We have to understand why do you get Q of 0.6. Okay, so now you can ask the question like what kind of things one can think of. It seems that if you can now higher redshift, you have much more data. We can split them into stronger absorption and weaker absorption and try to see like how they are evolving. And we are able to map this very nicely, saying that strong absorption cloud absorbing clouds cluster more strongly compared to weak absorption clouds. So one can ask the question, can you produce this evolution in the simulation? So this is what is shown here. Blacks are observing points. Blue curves are from our standard simulation where we use the background radiation as predicted by the earlier models. And you can see that we perfectly fit around redshift of 2. When you go to higher redshift, the clusterings are completely under predicted by these models. So if you really wanted to fit these blue curves, if you really want to fit these black points, what we have to do is that we have to enhance the radiation field. One of the methods.
Time is up.
It's done last. I have only one slide left. Yeah.
Okay.
So basically, then this curve, actually, I can put this curve on top of this data points by changing the radiation field. So the bottom line, I wanted to, okay, the same thing is explained here. I will go to the conclusions summary because this is exactly the same curve. We put it together from low redshift. So I just summarize in 2 slides. Low redshift IGM, what do we understood from this exercise? The measured UV background is consistent with quasar. There is no photon underproduction crisis. Reported detection of 3-point correlation. We report the 3-point correlation function for the first times. Simulation has some issues at small scale, which has to be sorted out. Gas contribution to the gas contributing to 3-point correlation are coming from large scale galaxy distributions. So they can be very good probe of how filamentary structure evolve as a function of redshift. This is one thing we are yet to embark on. Simulation do not produce B distribution as well as small scale clustering. When you go to higher redshift, this is my last slide. We measure UVB consistent with those coming from both quasars and galaxies, but you have to see there are some tweaks we have to do, as I explained later on. First time we have a very accurate measurement of thermal evolution of the IGM, which confirms the rapid evolution of helium-2 reionization at redshift 3, which requires non-equilibrium as well as some tweaking in the efficiency. And we report first detection of line of sight 3-point and 2-point correlation functions. And we are already saying that we may have constraints, further stronger constraints on the radiation field coming from these clustering measurements. So, okay, I think last part I don't want to go into. I think that's not correct. Okay, let me stop.
Okay, thank you. So I think we have time for a couple of questions. So is there any question in the chat box? I don't see any question. Is there any question offline? Okay. Okay, I do see questions now. So Suchetana Chatterjee has a question. Yes, please unmute yourself and ask. Can you unmute?
Yes, I could unmute now. Okay.
Okay.
Anand, just a clarification. If you go to your clustering, so there are a couple of slides. So can you hear me? Yeah.
Yeah.
So if you go, so the one where you do it as a function of redshift. Sorry.
Sorry, I'm not hearing you properly.
Can you hear me now?
Yes, loud.
Sorry about that. Yeah, I was busy. So was there something where you showed clustering as a function of redshift, or was it?
Yeah. This is a clustering as a function of redshift.
Function of redshift, right? Yeah.
Yeah. This so going redshift is given here. This is for 2.6 and 3.2.
Yes. So the question is that this is for which samples?
This is for high redshift quasar spectra with a shell spectroscopy from ground.
And like typically, what is the sample size?
We have about okay, I have given the details here. Because the number of quasars used is very high, but we have sampled them. This is the number of quasars you can see.
Okay, so no, I was wondering that, and so if you go to the plot, Anand, yeah, I was just maybe I was missing the spatial scale. I was thinking like, what is it? H inverse. Sorry, I couldn't read it. 3 megaparsec, is that what?
It is like 7-8 megaparsec for 2-point correlation.
Okay. Oh, 7-8 megaparsec.
2 megaparsec.
Yeah, I was wondering that because the error bars look like quite small. So I was wondering that how are these, can you just quickly explain maybe like how are these measurements made, the clustering?
You do this 2-point correlation like this, right?
Yes.
So basically you sit in, you go to any cloud and you calculate how many clouds are there with different pair velocities, pair separations. That is DD.
Yeah.
Then we know the total number of cloud along the line of sight. You take the same number and randomly populate along the line of sight and do this exercise for random. So you know that how many data pairs are there, how many random pairs are there.
That's right.
And you calculate this. And you can do the error in different ways, right? You can either do.
Yeah, that's what I was asking. That what are these error bars? How did you get
so
the
either you can have error coming from the bootstrapping exercise because you in the data thing, instead of using say we have about 200 sightlines, we can bootstrap within them and calculate what is the kind of error one gets from there, right? Or you can simply do root n error, which we don't do. We try to do the bootstrap.
Okay. Thank you. So yeah, I was trying to ask that because, okay, thanks.
So Nirupam commented that basically there are a large number of clouds along the line of sight, even if QSO number is not that high. Is that how the error bars are small effectively?
Yeah. I think that is why what is important is the table. What is important is the path length, and this is what one is talking about, right? So each quasar sight line, you cover quite a bit of redshift range, and a lot of absorption is present. That is the idea. Correct.
Okay. So is there any other question? I saw Pankaj was raising hand, but not anymore. So if there is no other question, then we'll move on. Okay, thank you, Srianand, for this wonderful talk. So let's move on to the next talk now, which is by Aratrika Dey. The title of the talk is a comparative study of the long-term optical and IR variability of high redshift, narrow line, and broad line Seyfert 1 galaxies. So Aratrika, you have 12 minutes for the talk and 3 minutes for questions, and I'll give you a 2-minute warning at the end of 10 minutes.
Okay. Can you make it full screen, please?
Yes, could you please make it full screen?
Is there a view option? You can.
Yeah, it can be done. It's not. Yes.
Okay. Full screen.
Okay, so you can start.
Yeah, this one. It's okay. You can manage the rest. I suppose. Hello everyone, both near and far. So I'm a JRF at Indian Institute of Astrophysics, working under the supervision of Professor C.S. Stalin. Today I'll be presenting my ongoing work titled A Comparative Study of the Long-Term Optical and IR Variability of High Redshift, Narrowline and Broadline Seyfert 1 Galaxies. Now the question that I'm going to start, yeah, sorry, mic, okay. Hello, is better, right? Yeah, okay. So I'm going to start with the question that what are narrowline Seyfert 1 galaxies? So narrowline Seyfert 1 galaxies are a special class of active galactic nuclei that were classified in 1985 by Osterbrock and Probe. They were discovered earlier, but this classification came about in 1985. Now these are characterized on the basis of their optical spectrum, on the basis of the broad component of the HBT emission lines having a full width at half maximum of less than 2000 km per second. They show weak O3 emission and strong Fe2 emission lines. They are also found to show strong soft X-ray variability and steeper X-ray spectra as compared to their broadline counterparts. Now we haven't yet reached a consensus on the nature of their black hole masses, but it is generally thought that the black hole masses range from 10 to the power 6 to 10 to the power 8 solar masses, and these are mostly found to be hosted by spirals. Narrow-line Seyfert ones also exhibit a high accretion rate, ranging from 0.1 Eddington ratio to super Eddington accretion as well. Okay, here I have shown three pictures. At the extreme left, this is the optical spectrum of a Seyfert 2 galaxy, and as you can see, there are no broad bases in these emission lines. This is a typical spectrum of a narrow-line Seyfert 1 galaxy, and here the FWHM of the H beta lines actually is less than 2000 km per second, but it is greater than the value that can be seen in Seyfert 2 galaxies. And coming to the broadline Seyfert ones, it actually exceeds the FWHM exceeds 2000 km per second. Now, coming to the nature of narrow-line Seyfert 1 galaxies, what we know so far is that almost 7% of them have been detected in the radio band. Around 2008, it was found that many of them, a few of them also emit in the gamma ray bands. So these actually indicate the presence of relativistic jets in these objects, which actually puts the jet elliptical paradigm in question. That is, jets can only be launched by elliptical galaxies. That sort of is questioned after these discoveries. Hence, it is important for us to further investigate the nature of these objects. Now, having said the background, I'll come to my work. So, in order to understand what actually causes the differences between these classes of galaxies, both narrow-line Seyfert 1 and broad-line Seyfert 1, one possible method of investigation would be to actually investigate their variability properties. So, keeping that in mind, I have tried to investigate the long-term optical variability properties of narrow-line Seyfert 1s in comparison with broad-line Seyfert 1s, as well as the infrared variability properties. Now, coming to the optical variability investigation of part of my work. So the sample of sources were taken from the catalog of high redshift narrow-line Seyfert 1s with the redshift ranging from 0.8 to 2.6. 0.8 to 2.6. Now these sources were cross-matched with the CRTS database in order to find their optical V-band data. Now, as control sample, I have selected a list of broadline Seyfert 1 galaxies that are matched with the narrowline Seyfert 1 galaxies in terms of redshift, G-band magnitude, and black hole mass. And those data were taken from the SDSS DR14 Quasar catalog. Now, a final sample consists of 1,753 narrowline Seyfert 1s and a control sample of the same number of their broadline counterparts. Now, for all of these sources, I have again cross-matched them with the first database in order to find out whether they emit in the 1.4 gigahertz range. These are the histograms of my samples of narrowline Seyfert 1 and broadline Seyfert 1s. Now, coming to the light curve analysis, the data from CRTS were inspected in order to remove the points with outlier points in flux as well as points with large error bars. I use the 3 sigma clipping algorithm. The CRTS data spans a period of 5 to 9 years. And in order to calculate the intrinsic amplitude of variability, I use this formula where sigma m is the what I am looking for. Okay. Here are two sample light curves from the analysis that I have done. In the left, there is a sample curve for a narrowline Seyfert 1 galaxy, and this is a broadline Seyfert 1 galaxy. Okay. Now coming to the results, what I have done is I have compared this sigma m with various physical properties of the sources. What I have shown here is on the left is basically the distribution of variability amplitude for only the radio detected narrowline Seyfert 1 and broadline Seyfert 1 galaxies. Now a clear shift is shown here. I'll elaborate the results in a later slide. And this one here is basically the distribution for the radio undetected ones. Yeah. Okay. Now this is amplitude versus log of jet power. I have tried to find out the correlations between sigma m and this jet power parameter, and also the black hole mass. The results I'll again come in a later slide. Now moving on to the second part of my work, which is the infrared variability. Here again, my sample of sources were taken from the same catalog, and these were cross-matched with the WISE database in order to find the data in the WISE bands. As control sample, I selected this list of broadline Seyfert-1 galaxies, again matched in redshift, G1 magnitude, and black hole mass. Now, my final sample consists of 1017 narrowline Seyfert-1s and their broadline counterparts. This is again with the distribution of my samples in black hole mass, G1 magnitude, and redshift. Coming to this part of the light curve analysis. So I've analyzed the data in two bands, W1 and W2. Again, I have removed the outlier points in flux as well as points with large error bars. I have also tried to investigate short-term variability by breaking up the data into chunks of 1.2 days. This is the formula that I have used in order to characterize the amplitude of in order to calculate the amplitude of variability. The only difference is that I have there's this systematic error term coming in, which has been calculated to be 0.024 and 0.028 values for W1 and W2 bands respectively. This I have taken from the literature. These are two sample light curves. For the left one is for a narrowline Seyfert-1 and the right one is for a broadline Seyfert-1. The bottom panel shows the W1 data and the top panel shows the W2 data. These boxes basically corroborate the 1.2 day chunk. Okay, so coming to the results, this at the extreme left, this is basically the distribution of long-term amplitude variability for W1 band, and this is the same for the W2 band for narrowline Seyfert-1 and broadline Seyfert-1 as well. And these are the same quantities for the short-term period. Now, as can be seen here, these are quite similar. Here, what I have done is I have plotted this W1 minus W2 versus W1 diagram for the same narrowline Seyfert-1 which is the light curve that I showed earlier, and this is for a broadline Seyfert-1, and this is the histogram for the slope of these lines that I have plotted for the narrowline Seyfert-1 and broadline Seyfert-1s. Similar to the previous work, I have tried to find out the correlations between the amplitude of variability and the physical parameters like radio jet power and the black hole mass for radio detected as well as radio undetected narrowline Seyfert-1s and broadline Seyfert-1s. Now coming to the conclusions. So as I showed earlier, I'll say about the optical variability results first. So most broadline Seyfert-1 and narrowline Seyfert-1 galaxies are found to show long-term optical variations. We also found that about 5% of our sample actually were emitting in the radio. I mean, it was available in the first survey. Now for the radio, it is actually radio undetected. For the radio undetected sources, it was found that both narrowline Seyfert-1 and broadline Seyfert-1 showed similar long-term optical variability characteristics, but that did not hold true for the radio loud sources, basically radio detected sources. It was found that the broadline Seyfert-1 galaxies are showing higher amplitude of variability as compared to the narrowline counterparts, which might have been due to the differences in jet power between these two samples. And it was also found that the jet power is actually higher in the broadline Seyfert-1 sample. And the curious thing that we noticed is an anti-correlation between the amplitude of variability and black hole mass for both these classes of galaxies in the optical variability part of my work, of course. Now coming to the IR part, it was found that not most, but majority of these two classes of galaxies showed long-term infrared variations.
You have 2 more minutes.
Yeah, okay. Almost 6% of our sample for both these classes were found to be detected in the radio. For both radio detected and undetected sources, it was found that there were similar intraday as well as long-term IR variability characteristics for both these classes of galaxies that I showed in one of the previous slides, the histograms. It was also found that long-term color variation actually showed the trend that they were redder when brighter for both these classes of galaxies. I mean, that was something that we saw for all of our sources actually. The correlations that I tried to draw with various physical parameters like radio flux at 1.4 gigahertz, corresponding radio jet power, black hole mass, all of that, those were calculated, but those were basically found to be inconclusive. Nothing could be inferred out of that. So yeah, that's all. Thank you.
Thank you, Aratrika.
Yeah.
So, is there a question?
Yeah, I think there is.
So I don't see any raised hand in Zoom. Is there a question?
Yeah, in the audience there is.
In the audience there is, okay. So then can you please repeat the question when you hear it?
Yeah, of course.
So you have plotted jet power versus amplitude. I want to know how you have defined amplitude.
Okay, yeah, I'll go to the slide maybe. So are you talking about the optical part or the IR part?
Like you plotted one.
So
It was an amplitude versus jet power in log.
So that's something I've done in both the cases.
So like any one of them.
Yeah,
how
yeah.
you defined it?
Yeah, this is how I have defined this amplitude of variability. So this is basically the variations on top of the error.
So this is like variability in the light curve. That is how you have defined amplitude.
Yeah.
It is variability amplitude.
Yeah.
Oh, okay.
Amplitude of variability.
Yeah, got it. Thank you.
Oh, sorry, did not repeat the question.
No, that's okay. We could hear it.
Okay.
So is there any other question in the audience? Because there is 2 raised hands in the.
There is another question.
Okay, please go ahead.
So my curiosity is that you have tried several parameters for both type of galaxies, but not yet you don't have any conclusive results, right? But from the parameters.
For the infrared, I don't have.
Yeah. So, but my point is like, what all are your expectations?
So,
why you wanted to put these parameters?
Yeah. So narrow lens Seyfert one and broad lens Seyfert one, we know like observationally that these are 2 separate classes of galaxies. But what drives this difference, that's still not clear to us. So the physical parameters like luminosity, black hole mass, accretion rate, these are found to be quite correlated with variability properties. So that's why I've investigated the variability properties and their correlation with these physical parameters, in order to find out that if some light can be thrown upon what actually drives the difference that we see in the spectrum. So that was the idea.
So does it say that there is no differences in terms of?
No, that I haven't concluded yet. So in the optical part of my work, I have seen some differences. For example, there is quite a clear difference in the jet power, but in the IR, there is no conclusions have been reached yet.
So should we move to the next question now? So Priyanka Rani has a question.
Excuse me, sir.
Sorry.
There is another question from the video.
Okay. So then should we, maybe the audience question, they can talk to the speaker after the session, and we should choose one of the Zoom questions or whatever you prefer.
So,
okay.
Okay. Yeah. One Zoom question maybe.
Okay, sure. So Priyanka Rani has a question. Priyanka, could you unmute?
Yeah, hi. Can you hear me?
Yes.
Yeah. So I have one question that how did you obtain this radio jet power and black hole masses for your sample? And another question is like, do you know like how many sources in your sample are known to have jets? Because
known to have jets. Okay. The second thing, I don't know how many sources have been known to have jets. That I don't know yet. But for the first part, radio jet, I have calculated using this data from first. So that has been redshift corrected, and I have used a formula that I haven't put here. So basically, I have calculated the luminosity distance. I know the redshift from the SDSS DR14 catalog, and I know the first flux density in the 1.4 gigahertz that central. That thing I know. So these things I have put together to find out the radio jet power. I don't know how to.
okay.
So should we move on to the next? So Ananda, so very quickly, Ananda Hota, you have a question?
Oh, another thing, Priyanka. The sources that I've used, that none of them have this have been detected in the gamma ray. That much I can tell.
Hello, can you hear me?
Yes.
Hi.
I may be interested in, I'm interested in spiral host large radio galaxies. My question is quick. Spiral host large radio galaxies I'm interested in.
Okay.
So you have said that 6% of your sources are detected in first radio data.
Yeah.
And most of these such sources are in spiral.
Oh,
What
that I
else
don't.
information you have?
This is actually part of my future work. So it was known so far that mostly narrow-line Seyfert ones as well as broad-line Seyfert ones are hosted in spiral galaxies. But after this discovery of jets, there has been questions about it, like whether spiral galaxies can also produce jets, or narrow-line Seyfert ones can also be hosted in ellipticals. So this is part of my future work. I like to find out what sort of the nature of the host galaxies of narrow-line Seyfert ones. So here I haven't said that all of these galaxies are spiral galaxies, because we don't know yet.
They're too far, simply, right?
Too far, yeah. Mine is a high redshift sample, so it might be difficult to actually resolve that much. So I don't know whether it's exactly because they're too far, but I think that is a possibility, that since these are high redshift sources, it might be difficult.
Okay. So Aratrika, we have to stop now. Please, if there are other questions, please talk to the speaker after the session. And we'll move on to the next talk now, which is by Jyoti Yadav. It's on discovery of a triple AGN in the NGC 7733-7734 merging group. This talk will be through a recorded video. Okay, so the volunteers will now play the video, and then at the end, I guess the question session will not be there because probably the speaker is not present. Is that right? Okay, so please play.
Hello everyone, I am Jyoti, and first of all, I would like to thank the organizers for giving me.
I cannot see the video. I can hear the voice, but. So yes, now I can see. Yes.
Hello everyone, I am Jyoti, and first of all, I would like to thank the organizers for giving me a chance to present my recent work in this meeting. I will discuss about my recent work on the discovery of triple active galactic nucleus in NGC 7733 and 34 merging group, and I have done this work with Moshmi Das, Sudhanshu Barve, and Francis Combs. We know that galaxies grow through interactions and mergers, and based on the gas contents in these galaxies, they have been classified as wet mergers if the galaxies are gas rich, and dry mergers if the galaxies are gas poor. When the galaxies interact with each other, they exert tidal forces on each other, which could lead to cloud compression, which then triggers star formation in their nucleus as well as in their excretins. During the interaction, the gas from the outer disk can be pulled out, and it can be seen in the form of tidal tails. And we also sometimes see the formation of tidal dwarf galaxies along the tidal tails. We also know that every galaxy harbors a supermassive black hole. So when the galaxies come closer, the black holes also come close, which then forms supermassive black hole binaries. And if the black holes in these systems start accreting gas, they can form single agent or dual agent system. So during the merger of two galaxies, sometimes they encounter a third galaxy. And if the black hole in that third galaxy is also accreting, they form a triple agent system. The link between the interstellar gas physics, large-scale interaction, and active star formation in the interacting galaxies is very complex, and it is not fully understood yet. So it is very important to understand all these diverse processes using multivariate data. So to do so, we started a survey of 10 closely interacting southern galaxies, which shows evidence of star formation in their tidal tails as well as in the spiral arms of the individual galaxies. So we observed these galaxies using infrared survey facility telescope, which is a 1.4 meter telescope in South Africa. And this telescope is capable of simultaneous imaging in J, H, and K bands. To study the star formation activity in these galaxies, we observed these galaxies in far ultraviolet band using ultraviolet imaging telescope data. So the FUV data combined with our NIR data will help us to study how the stellar masses of these galaxies grow during interactions and what is the effect of interaction on the star formation activity in these galaxies. We also found archival MUSE data for these galaxies, and MUSE is an integral field spectrograph on very large telescope, and MUSE provides 3D spectroscopic data with very good resolution. So using MUSE data, we can get gaseous kinematics, stellar kinematics, star formation history, line strength, and many other properties of the galaxy. So these are the NIR images of some of the galaxies in our sample. And from here, you can see that some of the galaxies are interacting at some distance, while some of these galaxies are in the advanced stage of merging. So we started with the Galaxie NGC 7733 and 34. And here the left image shows the interacting galaxies NGC 7733 and 34. So both the galaxies are barred and they are at a distance of around 150 megaparsec. And these galaxies are separated by a distance of around 48 kiloparsec. And both the galaxies show molecular gas in their disk. This is the multi-wavelength image of the galaxy pair, and this is 7733 and 34. So the left panel shows the FUV image of the galaxy, and FUV traces star formation up to around 10 to the power 8 years. The middle panel shows the H-alpha image of the galaxy collapsed from MUSE data, and H-alpha traces star formation up to 10 to the power 6 years. So both the FUV and H-alpha image shows that these galaxies are going through an ongoing recent massive star formation. And the right panel shows the J-band image of the galaxy, and J-band traces the all stellar population in this galaxy. We also noticed that there is a FUV bright clump present in the southern part of the galaxy, and this is 7733, and it is connected to the galaxy, and this is 7733 via an FUV bright bridge. The redshift, the spectroscopic data of this galaxy is not available, hence we could not confirm the redshift of this source, but this could be a possible candidate merger with this system. So our aim in this study was to look at the effect of interaction on the star formation and AGN activity in this galaxy. So to do so, we looked at the BPT diagram. So the BPT diagram was named after Baldwin, Philip, and Talbridge. And it is a set of emission line diagram, meaning based on the ratio of the emission lines, we can tell about the source of ionization mechanism of the ionized gas, whether the ionized gas is coming from a star forming region or whether it is coming due to an AGN. So here the left panel shows the BPT plot of the galaxy NGC 7734. And here we see that emission from the central region lies in the linear part of the BPT plot, which suggests that this galaxy hosts a linear type AGN. The right panel shows the BPT plot of the galaxy NGC 7733, and here we see that the emission from the central region lies in the Seyfert region of the BPT plot, which suggests that this galaxy hosts a Seyfert type AGN in the center. We also noticed the Seyfert type AGN along the minor axis of the bar. So to confirm whether this Seyfert type emission along the minor axis is actually associated with the AGN, we created a color composite image shown in the bottom right panel. So here the blue shows the H-alpha image, and red shows the N2, and green shows the O3 emission. So here we see that there is an extended O3 emission present in the northeastern region of the galaxy. So this is basically an extended narrow line region which is associated with the photoionized gas around the AGN, and we found that the extent of this extended narrow line region is around 18 kiloparsec. While working with this galaxy in the J band, we noticed that there is an unusually large clump present in the northern arm of the galaxy NGC 7733, and this clump has been identified as a star forming region in the previous studies. And then we looked into this clump in more details, and we did the optical decomposition of this clump, and we found out that the effective radius of this clump is around 3.2 arcsecond, which corresponds to around 2.4 kiloparsec. So such a large value of the radius of this node did not seem like us to that it could be a star forming region, but it suggested that it could be the bulge of a galaxy. And we also noticed that there are tidal features associated with this clump in the H-alpha and FUV map. So to confirm that whether this clump is really a star forming region or it is a separate galaxy, we looked at the velocity profile of the galaxy NGC 7733. So here we see that most of the velocity field shows the feature of a typical rotating disk with the Doppler shifted blue and red velocities. But in the rectangle, we see that the velocity of this knot is clearly different from the velocity field of the disk, which suggests that this clump is not a part of the galaxy NGC 7733, rather it is a small separate galaxy which is merging with the galaxy NGC 7733. Since this object is present in the northern arm of the galaxy NGC 7733, we named this object as NGC 7733N. We also looked at the AGN activity in the center of this galaxy NGC 7733N. So since this galaxy NGC 7733N is along the northern arm of the galaxy NGC 7733, in the emission lines, we also see the contribution from the galaxy NGC 7733. So here from the figure, you can see that there are two sets of emission lines. So the blue is coming from the galaxy NGC 7733 and the red dashed line is coming from the galaxy NGC 7733N. And we fitted the Gaussian profiles in these emission lines and extracted the fluxes and plotted the PPT diagram. So here we see that the contribution from the NGC 7733 galaxy lies in the star forming region. So which we expect because it is coming from the spiral arm and we expect star formation along the spiral arm. While the emission from the NGC 7733N lies in the Seyfert region, which suggests that the galaxy NGC 7733N also hosts an AGN. Hence, our triple interacting system hosts a triple AGN. And we also looked at the black hole masses in this system. We found out that the black hole masses in the galaxies NGC 7733 and 34 have a similar range of values of around 10 to the power 8 solar mass black hole, and they also have comparable stellar masses. NGC 7733N hosts the least massive stellar disk and the least massive black hole having a mass of around 10 to the power 7 solar mass. So these are the implications of our study. Dual AGNs have been detected in many galaxies, but triple AGNs are rare. And our study shows that multiple AGN system can be present in galaxy groups that show ongoing mergers. And these galaxy groups are fairly common, so they can be good targets for detecting multiple AGNs. Enhanced AGN feedback in galaxies are relatively unexplored, and it plays an important role in building hot gas reservoirs around galaxies, especially at early epochs when galaxy mergers were more frequent. And this feedback can heat the intracluster medium in clusters and can enrich the circumgalactic medium around galaxies. Triple AGN systems such as the one that we have detected in NGC 7733 and 34 are ideal laboratories for studying the growth of hot gas, AGN feedback, and supermassive black hole growth in mergers, and it should be relatively common in gas-rich galaxy groups. So this is the summary of our work. We found the AGN activity in the galaxy NGC 7733 and 34, and we also detected extended narrow line region in the galaxy NGC 7733. We also discovered a new galaxy along the northern arm of the galaxy NGC 7733, and we named it as NGC 7733N. We also found out that NGC 7733N also holds a Seyfert kind of AGN. We also noticed a potential bridge between the galaxy NGC 7733 and 2 Mars 2342 in the UV map. However, we need redshift estimation to confirm whether this galaxy is merging with the galaxy NGC 7733 and 34. And our study suggests that triple AGNs are rare. However, their detailed study could enhance their observed frequency in groups, and especially at high redshift. Although our study focuses only on one system, the results suggest that small merging groups are ideal laboratories for studying multiple AGN systems. Thank you. Unfortunately, I cannot be present live to answer your questions, but if you have any questions, please contact Moshmi Das, or feel free to post your questions on Slack. I'll be happy to answer your questions.
Okay, so thank you volunteers for playing the video. And I think as she explained, if you have any question, you should write to her in the Slack channel. Or if you are in the conference, you can talk to her collaborator, Professor Mousumi Dash. Okay, so let's move on to the next talk, which is by Krishna Mohana. And the title of the talk is Long-Term Multiband Monitoring of Blazar 3C66A, Evidence of the Two Distinct States with Different Baseline Flux. So Krishna Mohana, could you please share your...
Can you hear me?
Yes, I can hear you.
I will share the screen.
Yes, please. Yes, we can see the screen now. Yes, we can see the presentation.
Okay.
You're in full screen.
Okay. Good evening to all. I am Krishna Mohana, final year PhD student at Manipal Center for Natural Sciences, which is under Manipal Academy of Higher Education. And at foremost, I thank the organizers for giving me an opportunity to present our one of the published work titled Long-Term Multiband Monitoring of the Blazar 3C66A, Evidence of the Two Distinct States with Different Baseline Flux. So I would like to also thank the co-authors of this work, who is Dr. Dibijoy Bhattacharya, who is also my PhD thesis supervisor, and Ranjiv Mishra, Subir Bhattacharya, and Nilay Bhatt. So I will give a very brief introduction to the what is blazar. Actually, if you look at the figure 1, which is actually a schematic representation of the active galaxy, where you have at the center supermassive black hole, and around it there is a accretion disk, and there are relativistic jet kind of structures which are emanating from this central region. And over the several decades, different kinds of active galaxies have been observed. And under the unification scheme of proposed by Urey and Padwani, there's one particular class of active galaxies which are very bright, and they are called as blazars, where the relativistic jets is making a very small angle with the line of sight of the observer. Blazars are very bright in gamma rays, and it is very well known to show variabilities in gamma rays from minutes to hours to months to and even year time scale. And if you look at the figure 2, this is one of the typical gamma ray light curve of the blazar 4C21.35. I just wanted to emphasize on that as you can see that the flux sometimes goes very high, which is called flaring activities, and then comes down and remains in the low activity or the quiescence for a long period of time. So people have tried to address the emission mechanism and possible physical scenarios for such activity states over the several decades, but still there are some questions for which the answers are not fully understood based on the observation properties. Now, what is the motivation for this work is that the study which was carried out by Bhattacharya et al. 2013 and 2017, what they notice is that there is a factor of more than a factor of 10 decrease in the average gamma ray flux for a few of the egret. Egret is an earlier gamma ray mission which was 1991 to 1995, and Fermi was which is from 2008 and still it is in operational. As you can see in the figure, what we are asking is that is there any such kind of a baseline or average flux transition that could occur in these blazar light curves. So their study suggests some sort of could happen in the sense that could occur, and that could lead to the decrease in the average gamma ray flux activity. In the recent times, with the decade-long observations, one of the few works have been reported. One is in a blazar 1ES1215+303 by Valver et al. 2020. As you can see in the figure 4, what they see is that they see some kind of a gradual increase in the baseline flux of the gamma source in the gamma ray band, as well as also they see in the similar trend is also seen in the optical band. However, their study could not give any conclusive interpretation why this is such gradually it is increasing, and they also try to look whether is there any jet precision which can cause such gradual increase in the baseline activity, which they reject this the hypothesis because their observations are not using the VLBI is not inconsistent with what they observe. And also there is another study in the another class of active galactic called as misaligned active galaxy, where in the NGC 1275, as Gulati et al. 2020, what they report is that there is also some kind of a baseline increase during the activity states, but due to the short-term fluctuation, they could not identify the clear transition zones in this particular source. In our study, which is a blazar 3C66A, what we see is that in this figure, it is a weekly averaged gamma ray light curve. We see qualitatively there is some kind of a transition in the gamma ray baseline, which is happening around 2011, in June 2011. And the solid horizontal line is the average flux of this particular source, and the dotted dashed lines in the blue and the green are what we term it as the average flux for the state which is before the transition, and average flux for the state which is after the transition. And using the cumulative flux of this gamma ray light curve, we found that the transition is happening somewhere around June 9, 2011, and we define the source to exhibit a baseline transition change, which is from state A to state B. Now we looked at in the multi-band light curve for the other energy bands. As you can see, is that the first one in this diagram is the gamma ray light curve, second is X-ray, third is UV, and fourth and fifth and sixth are in the optical band. The optical data that is from the Stewart Observatory clearly indicates that there is some similar kind of a trend is also seen in the optical band. Further, we study what we study is that we try to address the quiescent behavior of this source in the gamma ray band, where we consider those time periods where the flux is less than or equal to the average flux of the during the particular state in the state A and the state B, and we term this quiescent phase as SAQ and SBQ. From the gamma ray analysis, we find that similar like that of the state A and state B, we find there is a gamma ray flux is decreasing by a factor of 2 from state A to state B, even in the quiescent state. Now we investigate what could be the possible reason by using by constructing the broadband spectral energy distribution. We used a single zone electronic self-synchrotron comptonization model, where the results is shown in the figure 8 and figure 9 for state A and the quiescent states. What we noticed that keeping all the other rest of the parameters fixed from state A to state B, by only tweaking the changing the Doppler beaming factor, we could able to explain the low activity, the baseline flux change from state A to state B. Now Doppler beaming factor could arise due to change in the Doppler beaming can happen due to the increase in the jet inclination angle by 1 degree. Say for example from 1.7 to 2.5. In this particular case, and or else the decrease in the bulk Lorentz factor by around 25%. And what we see is that is such a scenario could be possible in the blazars, because in blazars we don't have a very good radio observations to check for the jet weaving angle, because it is most of the emission is jet dominated, and it is not highly resolved, unlike the other misaligned galaxies. There is one particular study where they see that variation in the position angle of in the jet in the parsec scale, particularly in the blazar. The figure 10 shows that it is more than 12 years of observations using a VLBI network, European ULBI network. What they see is that for one of the blazar source, two of the blazars, they see the position angle changes almost like around 1 degree. And further also there are some of the many radio galaxies show such properties. And other thing is that in the kiloparsec scales in some of the active galaxies, people have seen the curvature in the jet, which is shown in the figure 11. Then what we see is that we look at the literature, is the 3C66 our blazar has any radio observations, then we could find that from JAW till 2015, what we found is that from the VLBI radio morphology, we see that there is a two bends in this particular jet around 1.2 MAS and 4 MAS from the core. And we considered the average jet weaving angle of 1.7, which is taken from the Josted et al. 2017, and we calculated the projected distance and also the deprojected length down the jet where this bending is corresponding in the linear scale. It is coming around 200 parsec for 1.2 MAS and 700 parsec for the other 4 MAS value. And the transition time, that period, what we see is that around a month time scale. If you consider this time scale, and if you try to calculate what is how far the blob has moved in this time month, that comes around roughly 10 parsecs in the AGN frame. So this implies that after a few hundreds of parsec in this 368 jet bends sharply over a very small region around 10 parsecs by around 1 degree. So this could explain the observed.
You have 2 more minutes.
Yeah, I'm almost done. Month scale time transition period of the baseline flux. Also, we are not excluding the alternative thing is that the blob and the jet could have slowed down, and it is also possible that the reduction in the bulk Lorentz factor could have happened by around 25%, which can also explain the change in the baseline flux from state A to state B. I have shown here figure 13, the schematic, roughly the schematic diagram, what is happening in this particular 360 just. This is first time we are reporting in blazar, unlike in the Valverde 2020, where they see the gradual increase. Here we see that there is a transition in the baseline flux where the flux is nearly constant for roughly 3 years and then decreases to remain in the long period after the transition for 8 years. So what is the future scope of this work? Of course, this is done for one particular source. We have from the literature that there are people have reported helical jet structures and wobbling motions in the which have been seen in the high angular resolutions of the radio images in the galactic and extragalactic objects. And also Joshua 2017, they suggest that their observation suggests that there is a hint that in the BLAC objects very close to the jets, they due to strong curvature which the deceleration of the blob could lead to the due to the bend, the deceleration of the blob could happen. And we have right now Fermi-LAT with more than 2,000 blazars, and decade-long observation is available. A careful investigation for a list of the careful investigation in the to look for the baseline flux transition for a list of a bright gamma ray well-monitored source is required, along with the observations, VLBI high-resolution observations to understand these jet morphologies, how they are going to play either the baseline flux transition or the long-term variations in different classes of blazars. So I would like to thank Dr. TMA Pai PhD program, and authors are acknowledged to acknowledge the financial support of the ISRO financial support from the ISRO under the AstroSat Archival Data Utilization Program. Also, I would like to mention, bring to you all people one notice is that I am about to finish my PhD, about to submit a thesis in a couple of months, and right now I am looking for the postdoctoral positions, which especially I would like to work in the blazar related problems. If anybody is interested, they can contact me. Thank you. Thank you for the opportunity to share this work.
Okay. Thank you for the talk. So is there any question in the audience?
Hi. Actually, can you switch to the slide in which you
showed
the change in the average flux?
Change in the average flux. Okay.
It was the third slide of it.
This one?
Yeah, this one. So
Yeah.
is it an averaging effect, or have you looked at final binning of the low state, I mean the state B? Is there enhanced flux in state B if we do a final binning of this light curve?
Yeah, this is for that, is it driven by the flaring activities or the other fluctuations? What we did is we also studied the quiescent behavior. Quotient behavior, what we did is that we did not include those fluxes, the time periods in the data, where the flux is greater than the average flux. We only considered either it is lesser than the average flux in the particular state or lesser than, equal or lesser than that. That means that automatically it removes all those flaring activities. So from the gamma ray analysis, we find similar flux variations. The average flux variation is changing the quotient behavior.
In state B, you have excluded all those points when the flux is exceeding the average flux.
Yes,
you
yes,
have defined the average flux with the green line.
yes.
Okay, so it is a discontinuous data, and you have developed the
No,
spectrum.
yeah. Discontinuous data in the sense all these red color data points, they are detected points. These are 3 sigma detected, weakly detected points. These are detection points. In between, there are upper limits. Those upper limit data points I have not included. So what happens is that there is one particular technique in the Fermi lat. It is called a sum likelihood analysis, where you can at a different time interval, if the data is in the different time ranges, you can choose those time intervals and do the analysis. So that is what.
Okay, and I also want to know that how have you concluded that there is a change in Doppler factor from the spectrum analysis, from the spectrum that you developed?
Yeah, what we did is that we try to keep the parameters from the state A and state B exactly similar, and we changed, tweaked only the Doppler beaming factor, and this Doppler that could changing the Doppler beaming factor itself could explain the state A to state B. And I will also bring you your notice that the people can ask how about the Lorentz factor and the theta. These two values we have actually constrained from the radio observations. We have not changed that. We didn't change that fact, because if you change this, automatically your delta will change. Then we looked for this delta has two factors. One is Doppler beaming, this bulk Lorentz factor, and theta. This variation is very consistent with what is observed in the radio observations.
Okay, so I think we have to move on now. So we'll have one question from the Zoom session. So Amit has a question. Could you please just ask one question, and Krishna, could you please keep the answer to the point?
Yes, yes.
Sure, Ritaban. Yeah, hi Krishna, very interesting work. I have one thing which I'm quite interested, that you showed that your blob or the jet is getting bended around 700 parsecs, right?
Yes.
Yeah, so if you take, you are trying to explain your SEB through synchrotron self-Crompton emission. So let's say if you start with some particles, if they travel that much distance, they will lose their energy. And probably you need to have the magnetic field as well as your particles to be accelerated. Your blob should not expand, so magnetic field get diluted. So how you are managing this in your model?
So this is not a temporal model. Actually, this is a static model. And what we did is that we are not claiming that it is the blob is bending at 700, the blob is moving at 700 parsec. We are saying that it could either go through any of these 100 of a parsec. This is just a roughly, it is not a strong claim. I know that after a certain parsecs, the blob can lose the energy. So that is what we are also saying, that the change in the bulk Lorentz factor itself could itself can explain this one. I understand your question, but we are not strongly claiming on the what is this the jet is one of the scenario. We are saying that it could be the one of the possibly the one of the scenario. So
okay.
We have to further look for many other blazar forces.
Okay, so I think we have to move on to the final talk now. And so if there are other questions, please contact the speaker after the session. And we'll move on to the final talk of the session by Ravi Joshi. The title of the talk is X-shaped radio galaxies, Insight from Optical Host Properties, Environment, and Radio Structure. So Ravi, yes. So we can see your...
Yeah, thank you. Yeah, thanks, Ritaban. So first of all, I would like to thank the organizers for giving me this opportunity. So I'll be discussing about our recent effort to understand the X-shaped radio galaxies. That will be primarily from the optical host galaxy perspective. And the collaborators are listed here. So what are the X-shaped radio galaxies? We know that the radio galaxies in general possesses radio jets, that is from the kiloparsec to the megaparsec scales. However, there is roughly 3 to 10% of radio galaxies, which shows a peculiar kind of morphology, which you can see here. So what you see here is that you see a jet showing the hotspots. This is like conventional FR2 kind of radio morphology, which I will call like primary or the active jet. And then other than this, you see a diffuse radio emission roughly at an angle of 90 degrees with respect to the primary jet. These are typically of like FR1 kind of morphology, and overall it makes a shape of X. So this class of radio galaxies are called X-shaped radio galaxies. So what we know about them, or how do they form? So there are many scenarios that have been proposed, and few like most discussed scenarios are, for instance, the backflow scenario, where you can believe that plasma from the hotspots will flow back to the host, and then it moves along a low pressure gradient direction, forming an X kind of structure. The other discussed model is jet reorientation model, where you can think that the diffuse structure, what you see here, this is nothing but the relic emission of previous jet activity. And because of the merger, probably the jet has been reoriented, and now you see the active jet in this direction. So, and this causes the formation of X-shaped structure. The third discussed scenario is probably the dual AGN scenario, where we know that the mergers are prevalent. So it's possible that a galaxy hosting dual AGNs may be launching their own jets in 2 different directions, which will lead to the X kind of structure. So, however, there is no consensus so far. The reason being is that there are evidences in support and against in all the proposed models. For instance, if you look at the backflow scenario, then it's been found this in several elliptical galaxies, the gaseous halos has been found, which extends like sometimes even larger distances than the optical counterpart. So this kind of halos may lead to the diversion of the backflowing plasma in a certain direction. The other evidence comes from a tight correlation observed between the position angle of the wings, which are mostly always found to be aligned with respect to minor axis of the radio galaxies. So this again supports the backflow model. The third scenario comes from the morphology of the X-shaped radio galaxies, which are preferentially found to be hosting FR2 kind of radio morphology, where you expect to see the hotspots. And even in simulations also, MSD simulations also, it's been found that for this FR2 kind of radio morphologies, if you have a preferred luminosity less than 10 to 44, so then this will lead to the X kind of structure. However, for some of the X-shaped radio galaxies, the wings are found to be even more extended than the primary jet. So this backflow scenario model is not able to explain that why in some of the cases the plasma which is flowing with a supersonic speed, how can it go like even further than the active jet? So this fails here. The another possible scenario is the jet reorientation model. So it's been seen in the observations that for some cases jet has been seen to be reoriented. For example, there is one of the examples. This is a double radio galaxies, and if you look at the primary jet of this galaxy and the newly launched jet, there is a difference in the angle between two. And if this angle is say is larger than certain number, this will appear like an X kind of structure. However, this model doesn't explain that why for these galaxies the primary jet should align with the major axis of the optical host. The third possible scenario is the dual or the binary agent scenario. So in this, so for example, if you believe that the diffuse radio emission, what we see here, this is a relic of the previous jet activity, and if you do the spectral index mapping, then now one should expect that the wings will have this steeper spectral index. However, this has been tested recently by Dharam in 2019 with using about 26 X-shaped radio galaxies. They compared the spectral index difference between the wings and the lobes. So what they found, surprisingly, is that sometimes the wings are relatively flatter than the lobes. So there is not much difference in the radiative pH between these two. So essentially, this doesn't support the jet reorientation model, or probably some other mechanism. For example, the dual or the binary agent scenario may be supported. So, however, all whatever like results I have discussed so far, these all suffers from the low number statistics. The reason being is that until recently, only about 100 X-shaped radio galaxies were discovered. So to understand like these formation of the X-shaped phenomena, we have recently tried to search for more such candidates. So for this, we have searched these systems at 1.4 gigahertz first VLA survey. This supplemented with the 150 megahertz TGSS GMRT survey. We have discovered about 290 X-shaped radio galaxies. And among them, we have classified about 106 systems as strong X-shaped radio galaxy candidates. So here are the two examples you can see for the strong X-shaped radio galaxy candidate. If you look at here, if you look at the black contour, these are the first 1.4 gigahertz images. And alone, based on the first images, it's difficult, or you would, it's difficult to say that they are having X-shaped structure. However, if you overlay the TGSS images, the X-shaped structure nicely comes out. So using this sample of 106 strong X-shaped radio galaxy, we try to look for various correlations based on the optical host properties. So first of all, we question the backflow scenario model. So for the optical host properties, we have used about 41 X-shaped radio galaxies for which the optical images were adequate to calculate the major axis of the galaxy. So what you see here is that this is the optical host and this is the major axis of the optical host is being plotted. And similarly, the position angles of the wings and as well as the active jet has been determined. So if you just compare the difference between the optical major axis with the wings position angle, that is being plotted here in the red histogram. So what you see here, the apparent thing is that the difference between the major axis of the optical host and the wings is mostly larger than 60 degree or say 40 degree. However, so this essentially like again supports the backflow scenario model. But we have found a few exceptional cases also. These are the counter examples where we found that the optical major axis is more or less aligned along the wings of these the radio structure. So this becomes basically, so one set of the systems supports the backflow scenario, but there are counter examples also. So this becomes essential to like test this scenario. The other thing, of course, one can plot the various observed quantity. For example, if you put all these galaxies in the oval Ledlow plane, which is nothing but the radial luminosity as a function of absolute magnitude, then you can see that all of them lie in a locus between the FR2 and FR1 kind of radio galaxies. This hints that probably these systems are transiting from one phase to other, but this needs more investigation. If you compare, for example, the lobe length of the active jet and the wings in these systems, so for 3 of the systems, we found that the wings are almost like factor 2 larger than the active jet. So this is interesting, and this may be like this kind of examples will be the best suited to test the various scenarios. For example, the twin AGN scenario or the backflow model. Well, further we look for see, as I said, like this, X-shaped radio galaxies are primarily hosted in the FR2 kind of radio galaxies. So it's interesting to compare how these X-shaped radio galaxies correlates with their classical FR2 kind of systems. So for this, first of all, we compare the black hole masses, and for this we have compiled about 61 systems from the Sloan survey, and compared it with the control sample of about 400 FR2 galaxies, almost at the same redshift. And this has been plotted here. So what the red stars, what you see, they are they represent the X-shaped radio galaxies, and the blue stars represents the classical FR2 system. The same has been drawn here in the histogram. So the red hatched systems belongs to the X-shaped radio galaxies. So if you compare the masses, so we found that these X-shaped radio galaxies are systematically lower in the statistical.
You have 2 more minutes.
Okay. They are systematically lower than the FR2 kind of systems. This hints that even a minor measure may lead to the jet orientation in this kind of systems. If you compare the mid-infrared properties of these systems, again, the convention is same, the red stars are the X-shaped radio galaxies. Then we found that almost 80% of these systems are having Y's color more than 1.5, whereas only 20% of FR2 galaxies show the redder behavior. So given they are red and probably they are abundant with the cool ISM and probably tracing the recent merger. So these two evidences support the jet reorientation scenario. Well, one can look for the large-scale environment as well, given that the large-scale environment will drive the shape of the jets. We try to compare it for the X-shaped radio galaxies along with the FR2 systems and FR1 systems, which is being plotted here. And you can see that for both the FR1 and for both the X-shaped radio galaxies and FR2 systems, they live in relatively poor environment with a richness of about 10. Whereas the FR1 kind of systems, they live in the high density environment. So there is some similarity between the X-shaped radio galaxies and FR2 systems in terms of the large scale environment. However, to understand more about these systems, we are following them with the various telescopes, with the VLBA and UGMRT. So here are a few examples I have shown. So what you see in the top panel, these are the 1.4 gigahertz first images and overlaid with the PGSS maps. And the bottom panel shows our recent 1.4 gigahertz UGMRT survey images. So now we are trying to get data like different frequencies to map the spectral index and try to constrain various scenarios. So in conclusion, I will just say that what we have seen so far is that we have seen that the optical and the radio position angle alignment study hints that the backflow scenario may be in the act. But however, a handful of the systems also show the opposite trends. So it will be better to investigate these systems to test the backflow scenario. In terms of the reddening of the X-shaped radio galaxies, they hint that probably reddening, as well as the masses of these systems, hints that probably they are we are tracing the recent mergers, and probably this is led by the jet reorientation scenario. And of course, the large-scale environment of the FR2 and X-shaped radio galaxies found to be similar. So we are following this, and we are following this with various telescopes to understand the various possible scenarios. Yeah, thank you.
Okay, thank you, Ravi. So, is there any question in the hall?
Hi, thanks for that nice talk, Ravi. So my question is, you said that you have about 250 candidates and you have 106 strong X-shaped radio galaxies, right? So
yeah,
it's about 6 or 7 more than the previously recorded about 100. So what is the criteria you use to classify as X-shaped versus some low axial ratio galaxy?
Yeah, so basically for the X-shaped things, we demand that given the first resolution, because these have been basically selected based on the first survey and supplemented with the 150 megahertz CBC survey. So we demand that the axis ratio, like the major axis, should be more than 10 arcsecond and the minor axis should be more than 5 arcsecond. That is the resolution of the VLA. And yeah, and as far as like the strong and the probable candidate systems, so we know that like when we go for the visual, that is like highly subjective classification. So we basically with 3 of our co-authors have independently checked those systems, and based on those flags, we have go for the strong and the probable system.
Okay, so is there any other question offline?
Yes, sir, there is a question also.
Yes, please go ahead.
Hi, Ravi. So this slide number 8, where you showed like your exit galaxies as well as FR1, FR2, and they all are overlapping. So just for the clarification, that you said that maybe it is somewhere in transition phase from FR1 or FR2. Am I correct?
Yeah. So what?
So how? Yeah. So so that's where I'm getting confused. That with what scenario or process you are thinking in that manner, that if it is transitioning from one to another.
Yeah. So if you look at basically this overlap domain, radial luminosity versus the absolute magnitude. So this line basically divides the two systems. And if you look at the average power of the FR2 the X-shaped radio galaxies, they lie basically in between these two. So that's why I said probably this is a hint that we have to just carefully check whether if they are transiting from one to other. Yeah.
So what are the physical processes can be involved? Like when you were saying transition, so I mean.
Oh, so by the transitions, I mean is essentially the aging of the electrons only. So yeah, but the time scales we don't know.
Okay, so Ananda Hota has a question online. So Ananda, could you please ask a question?
Hi, can you hear me?
Yes.
I guess, yeah. I have been thinking about this thing. One question I would like to say that people connect the wing direction with minor axis of the optical host.
Yes.
And it doesn't explain everything. And the backflow model, people are also supporting now because of this new meerkat image,
yes.
Very impressive image.
Yes.
What I find people are missing is the Gopal cited one of my paper on NGC 3801. The rotation axis of the gas people are not looking at very carefully.
Yes.
Because the 3801 is a kinematically decoupled core. The active lobe may be responding to the central part, but the outer region could be saved by the outer region's gas dynamics. So people should look at the rotation of the gas in these systems.
Yeah, I agree actually. So regarding this, we have basically, so that is basically essentially the kind of shell model, right? And you can have, so we looked like all these 290 systems for the deep optical images, that is from the DKL survey. And unfortunately, none of them host the shell, given the probably the redshift, the relatively high redshift of these systems. So
no. I'm not talking about stellar cells. What I'm talking about the gas dynamics there. So that at least there is a long slit spectroscopy done for the center. Okay. What is the rotation direction of the gas in the system? Gas and plasma interaction will be more stronger than the gas and stars, plasma and the stars in the system.
Yes,
gas
I
interaction
agree.
will be better. Yeah.
Yeah. So
okay, thank you. We will talk later probably.
Sure.
Okay, so Shubhendu Rakshit has a question. Shubhendu,
Hi Ravi. So nice talk. So I'm wondering, do you have any IFU observations on these sources?
Not really. I have not checked the literature for that, but I'm not very sure. We need to check.
Okay, or any like a long slit spectroscopy along the direction of the XF, like both direction in the cross?
No, like as Anand said, like this can be like one of the things for the follow-up, but no, because what we are relying mostly on the archival data right now.
Okay. And the masses that you mentioned, black hole masses, they are calculated by M sigma or how?
Yeah, these basically comes from the stellar velocity dispersion measurement.
Okay. Yeah. Okay. Thanks.
Yeah.
Okay. So I think I will. So that would be. If there are further questions, please contact the speaker after the session. I would like to mention that Pankaj Kushwaha made a comment to Krishna Mohana on the chat box. So Krishna, if you are seeing this, you could contact Pankaj and answer his question. Okay. So
thank you so much.
Volunteers, should I now just end the session then? Is there anything else that you announce?
You can end the session.
Okay, there is no announcement or anything. Okay. So this is the final talk. This was the final talk. So let me take this opportunity to thank all the speakers and also thank all the volunteers to so smoothly conduct the session. And I hope to see you again tomorrow in some other in the next parallel session.
Thank you, sir.
Okay, with that, let's